Good morning, everyone. Welcome to my talk. Obviously, welcome to SQL Bits as well. It's my first time here. So yeah, really excited to see a few of you here. I know it's a bit of change of pace for quite a lot of the other talks that are going on at this conference, but yeah, hopefully there'll be at least a nugget of information for some of you. So yeah, without further ado, my name's Daniel Harrington. I'm here representing Mars Pet Care. And today we're going to be talking about Gecko, which is an application we've implemented to achieve efficient data encryption at scale. So the agenda for today, bit of background about myself, Mars, and the Pet Care Data Platform. Then we're taking a deep dive into Gecko, which is our bespoke data encryption tool. And then another look at Gecko 2.0 and how we've extended some of the features and enhanced the performance. So a bit of introduction. So as I said, my name is Daniel Harrington. I graduated from the University of Bath back in 2019. And since then, I've worked at Mars Pet Care as a data engineer for around 2 years. And in my time there, I've worked solely on Gecko and also within the platform team as well. My partner in crime, Jason, unfortunately couldn't be here today. He's moved on to some more product type stuff, not doing any fun coding anymore. So yeah, he's not here today, unfortunately. But yeah. So a bit of background. So at Mars Pet Care, we're part of a broad and diverse family company. And we're constantly evolving. And you can see on the right there the sort of plethora of different businesses that Mars are involved with. We've grown from sort of humble beginnings as a pet food company back in 1985, called Chappie, now we're a full family of nutrition, health, and services businesses, including things like pet nutrition, so IAMS, Whiskers, and Pedigree, pet health, so veterinary services like Banfields, and also things like pet tech. So we've got a company called Whistle, which invented kind of like a Fitbit for dogs, which is quite cool. So we have quite a diverse range of different data that we're ingesting and working with. So in terms of what we actually do here in the data analytics team, so we manage a platform of anonymized data from across all of Mars Pet Care's different brands and businesses. We have an ingestion pipeline called Kite, and that's been working in production for a few years now, ingesting data from across these different business units, and that's formed what we call the basis of the Pet Care Data Platform, which is kind of like our bronze level layer data which we work with. On top of this, we've built engines and designed processes to enhance the business value and integrity. And one of the ones I'm going to be speaking about today is Gecko, which is our data encryption ecosystem designed for Spark and Delta Lake. So in terms of our mission with Gecko, whilst Kite formed a really good foundation for the PDP, we wanted to enhance this and make some really good improvements. And one of the key ones here was actually data removal. So we wanted to improve data removal and handle it in a more efficient, safe, and effective manner. We wanted to increase the overall security of our personal data in the PDP vaults. And also maintain the data structure. So when before we were having to remove data, actually physically going in and deleting data was messing with the data structure. So we want to maintain that and continue to provide analytical value to our data scientists. And so into Gecko now, automated data encryption. So the core concept behind Gecko is that we utilize row-level encryption, so not file level, not path level, actually row-level encryption for our data. And our encryption key storage is in a single Delta Lake table in our data lake. And the ecosystem is made up of two core functions. So we have Gecko crawl and Gecko delete. Gecko crawl was what's responsible for the actual encryption of the personal data. And Gecko delete is responsible for the deletion of data through the redaction of encryption keys. I'm going to take you through the architecture of these two now in a bit more detail. So Gecko crawl, so working from left to right, the first thing that occurs is the deployment of configs. And essentially what I mean by this is actually deploying encryption keys. Obviously, to do row-level encryption, we need encryption keys. So the first thing we need to do before we do anything is actually create those. Once we have that, we can kick off Spark jobs that thread at a source and table level for all the different business units that we deal with. And each table will then be encrypted in 3 different locations. These being a raw location, a schema verified location, and an output location. And that output delta table is actually what the bronze layer data is. It's all config-driven, dynamic, so we've designed it in a way that's infinitely scalable to new sources and tables coming on board. And it's all config-driven and integrated quite nicely into Kite. So as new sources and tables come along, we can literally just config those up and run encryption quite quickly. So into actually the key generation, essentially how it works is that we loop through each source and table that we've ingested, and we generate what we call a salt for each source ID. And the salt at a fundamental level is just a 16-byte binary string. And one thing to note is that we prioritize client IDs over primary keys. And the reason for this is that when we have to do data removal, typically we'll have to remove data associated with a client ID, not necessarily the primary key of the table. And you can see what this table looks like. Essentially, it has the data source that a source IDs come from, the ID, and the salt. So you might be thinking, why salt? Where's the encryption key come from? Well, we actually add another layer of security here. So we combine the salt with a password, a source level password, stored in Azure Key Vault. And these two things combined generate the encryption key. So the reason for this is obviously if anyone has access to the encryption key and they could read it in, they would actually be able to decrypt the data. So just adding that extra layer of security just gives a bit more peace of mind. In terms of how we actually encrypt the data, so we encrypt data in parallel through both using Databricks notebook threading and also Python multi-threading. And we encrypt those 3 locations that I mentioned earlier. And at a fundamental level, all that happens really is that we read in the data as a Spark data frame. We then join that to the ID salt table that I just showed you, which gives us access to the salt key for those source IDs. And then we run it through what we call a Fernet encryption UDF. And that's applied across all the personal data columns and utilizes the password and the salt key in order to actually encrypt the data. And what we're left with then is an encryption token for any personal data that exists in that table. Once we've done the encryption, we then do data validation. So this is firstly counts, so making sure that the encryption hasn't added or removed any data. And also run it through our decryption module to ensure that all the original data can be regained and nothing has been corrupted or lost. And it's at this point, once we've done the validation, that we overwrite the data. And you can see here an example of some data that's been encrypted. So all of the non-personal data columns have been left verbatim, but the column that contains personal data has just been replaced with this encryption token. So anyone that even had access to this table wouldn't actually be able to read in any personal data, so just highlighting the security element that we've added. In terms of the actual encryption process, so as I mentioned before, there's 3 different locations. 2 of these are in Parquet file format. And this had the added complexity of that we had individual files for each date of data ingested. And in some cases, we're having to encrypt each file path, which could be up to 600 in some runs. So really adding some weight and complexity to the encryption process. Conversely, our output table is of Delta format. And anyone doesn't know, this is kind of like Parquet with some additional metadata added. But what makes it nice and easy is just a single path to encrypt. And it was easily optimized. It was an easily optimized process by Spark. So some initial shortfalls when we were encrypting the Parquet files, we were having to loop through file by file, which is obviously incredibly inefficient. Because data wasn't partitioned well and utilized across the cluster, this meant that the cluster was operating at a really low CPU percentage, which you can see from the graph on the right. And runs were taking an extremely long time. And unfortunately, with Databricks, you're not charged with how much CPU you're using. Once the cluster's on, you're charged for that cluster. So the longer the run takes, the more energy you're burning, and also the more money you're burning. So this was a clear point that we had to improve. To address this issue, what we did was we increased the number of shuffle partitions, which removed some of the effects of skew in the data, and ensured that we were operating at a maximum Spark parallelism. We also implemented Python concurrent futures, which allowed us to execute encryption logic for multiple Parquet files across multiple works in parallel. And as you can see from the graph on the right, the performance benefits was huge. We massively increased the cluster utilization and reduced the runtime from literally days down to hours. So moving on to Gecko delete now. And the best way to sort of describe this is like an illustrative example, so I'll take you through that now. So what would happen is we highlight an ID that needs to be deleted. We then simply add that into a web form, which triggers a logic app. And you can see some example data here. So we've identified this client within a vault. All of their personal data has been encrypted, and all of their non-personal data just stays as is. But as you can imagine, this isn't the only row of data that they have. They might exist in multiple tables across lots of different locations in the lake. So ordinarily, if we wanted to delete this data, we'd have to go to each of those locations and perform hard deletes on those rows. All we have to do now is go to the ID salt table and filter for that ID and simply redact the salt. And that's as simple as it is, really. So without the salt ID, the encryption key can no longer be generated. And from this point onwards, removing a single record from a single table, from this point onwards, the personal data can never be retrieved because once the encryption key is gone, it's just gibberish. And what's important as well is that all the non-personal data stays exactly as it was in the vault. So just proving that we've maintained that overall integrity and business value. So moving on to Gecko 2.0, looking at some of the features that we've added. So first of all, there's the issue of data control. So before you could either encrypt data or you couldn't. What we've introduced now is actual project level control. So each project can only access the data that they've been authorized to access, which is a really nice feature. This access control is controlled via password. So each project will get a password based on the activity that they've been authorized to use. So, for example, marketing projects will only have access to a marketing password and be able to decrypt that data. And also in terms of deletion options, before we could only delete data, whereas now we can actually control the activity that the data is used for. So this required some quite drastic architectural changes. And don't worry, I'm going to do a worked example, but I'll take you through this diagram first. So what we have now is the concept of a preference center. So this is where we store user preferences. So when data comes in, the first thing that we do is apply default preferences. And this typically assumes the minimum level of preferences, i.e. opted out of marketing, opted out of analytics, etc., just to ensure that we're not assuming anything about our customers. We then want to update the preferences table to represent the real world, and this can be done via either a preferences table at source. So Whistle, for example, provides us with a table that says this user is actually opted in for analytics, and we can update that. We can update to represent that, or the previous method as well. So actually individual requests coming through, there might be deletions or opt-outs. And then off the back of this preferences table, we can then create not just the ID Salt master view, but actually different views of that table. So we have an analytics view, a marketing view, and ... This can be infinitely extended to any type of view that we might need to create in the future. And then each project, as I mentioned, will have a password which will give them access to those particular views that will allow them to only decrypt data that they've been authorized to work with. So I'll just take you through a worked example because I understand that is a little bit convoluted. So if we get this user come in, ID 123, the first thing we do is apply the default preferences. So we assume that they're opted out of marketing and analytics. We then actually go to source and they say, actually, this user has opted in for analytics. So we go, great. We update our preferences center to represent that. So this user has technically opted out of marketing and opted into analytics. We then go ahead and generate the different views of the ID Salt table. So we're good to keep their encryption key in the master view. But in terms of the marketing view, this user's opted out. So we actually redact their encryption key from this location. But because they've opted in for analytics, we leave their encryption key in verbatim. And what this means is that if an analytics project came along and wanted to decrypt some data, they would only have access to the analytics view, so they would be good to go ahead and decrypt. But if a marketing project came along and tried to decrypt, they wouldn't be able to. So just highlighting how we can actually control at a project level who can access what data. So the benefits of this are obviously activity level control, infinite extensibility to new activities. So if a new requirement came along, for example, like A/B testing or any other requirement for different activities, we could just extend that by adding a new view into our ecosystem. And we've also retained all of the original functionality. So we can still do deletes. We can still do everything that we did before. We've just enhanced the ecosystem, really. So really sort of in conclusion, just thinking about the benefits. So the first, of course, is security. So every instance of an individual's information is encrypted. So even if someone maliciously gains access to the data, they won't actually be able to read any personal data without access to our decryption module, the passwords, and the encryption keys. Speed, so a single filter and redact is as simple as it gets, really, for data removal. We don't have to go and find lots of instances and track where we've actually performed deletions. Tractability, so our config contains metadata about the encryptions we performed and also the deletions performed as well. So we have a clear record of what data we've deleted and what data we've encrypted. Automation, as I mentioned before, we can just simply configure new sources. Really simple to set up new jobs. There's not much manual user input in order to get these jobs running, so quite a nice automated process to handle this. And data integrity, so by not actually deleting any rows, we maintain that data structure and ensure that our analysts have access to high quality data in order to do their analytics. In terms of future work, there's a few pieces that we want to try and do. The first of these being an API layer over key access. And this will enhance the speed of key access and also security. So by logging in the API, we can see who's accessed what encryption keys and why. The second of these is quite a key one. So you might be thinking, well, we have two completely separate processes, so ingesting the data and then encrypting over the top of it. It's very inefficient, and I agree. The reason was that Kite was already quite a well-established production ingestion mechanism, and we didn't really want to plug in at the risk of damaging that. So The next step is actually to integrate the encryption directly into the ingestion process. So we encrypt only once rather than having to go over and encrypt everything again. And the final of these is an enhanced encryption mechanism. So the Fernet encryption UDF that I alluded to earlier can be quite inefficient, as it's a Python UDF being applied to a lot of different, to all the rows essentially. There's two things that we could do here. First, these would be implement Scala encryption. This would reduce the serialization costs associated with using Python UDFs. And secondly, would actually be clever sort of pre-filtering of the data to ensure that we're only encrypting rows that need to be encrypted rather than running lots of sense checks on every single row. And yeah, that's pretty much it for my talk. I hope you found it interesting. Yeah, I welcome any questions after the talk. And also any feedback as well. Just scan the QR code or go to this address and you'll be able to provide feedback. Yeah, good feedback only. So yeah, thank you very much. Hope you enjoyed it. Updates, in terms of updating what? Yeah, so with Kite, we, because it's kind of like bronze layer, we just incrementally ingest lots of data. So we'll actually have like lots of rows for that user. So potentially if their address updates, we'll just get a new row of data with the same ID, but a different address. And because they're encrypted using the same encryption key, any deletes that are associated with that ID will be handled inherently when we get rid of it. Sorry, I can't hear. Sorry, Jack. Yeah. Yeah.
Is that for compliance? And if so, do you have to delete the underlying parquet in that raw layer as well that you loaded from?
Yeah, unfortunately, my hands are a bit tired with the actual legalities of it. But yeah, read between the lines. We don't actually have to delete the actual files. We're just literally deleting the key. And because the personal data is redacted, then it's fine because that can never be retrieved. Yeah, you can never retrieve it. Okay. Cool. Yeah, any more questions? If not, then feel free to come grab me afterwards. We can have a chat about anything. But yeah, thank you very much for coming. Hope you found it useful. And yeah,